In this video, we'll be talking about the units and a bit of background to actually measuring temperature. So what is temperature? Well, essentially what we're trying to quantify is the amount of thermal energy in something. And we quantify that as how hot or cold that particular item is. Now, the basic thing that we use to measure temperature is a thermometer. And there's lots of different types of thermometers. So we'll be discussing those in a little bit of detail. And we've got a few different scales that we can measure temperature over. Here's the three most common ones. The Rankine scale is another one as well, but it's less frequently used. So we have Celsius that we normally use most commonly when we're talking about what the weather's going to be outside to how hot we need to cook our food at. We typically use the Celsius scale. And I should note that this previously was called the centigrade scale. And centigrade meaning 100, and talking about there's 100 points between the point that water freezes and the point that water boils. Then we have the Fahrenheit scale. Now the Fahrenheit scale used to be used quite commonly throughout the world. But about 70 or 80 years ago, it fell out of favor for the much more simple Celsius scale that we use. Now, some countries like the US still use it, but by far Celsius is more common these days. And the other scale that we have, which is used more for scientific applications, is the Kelvin scale. One thing I should mention with the Kelvin scale is that we don't call it degrees Kelvin, we just call it Kelvin with a K to denote that we're measuring temperature in Kelvin. And I should also note that when we talked earlier on about the different base units in the SI system, Kelvin is one of them, and Kelvin is the scale that's used for temperature. Okay, let's look at how we convert between each of those scales. Well, Kelvin to Celsius and Celsius to Kelvin is quite easy. So 0 degrees Celsius is 273.15 degrees Kelvin. And likewise, 0 degrees Kelvin, which is absolute zero, we'll talk about in a moment, is minus 273.15 degrees Celsius. So we can just do a basic subtraction or addition of 273.15 degrees, and it'll get us from Celsius to Kelvin or Kelvin to Celsius. Now, to get from Fahrenheit to Celsius or Celsius to Fahrenheit, we're subtracting or adding 32 and then multiplying that by 5/9 or 9/5, depending on whether we're going from Celsius to Fahrenheit or Fahrenheit to Celsius. And if we want to go from Fahrenheit to Kelvin, we first essentially convert to Celsius and then add our 273.15 degrees. So here you can see the different thermometer ranges for each of these temperature measurements for Celsius, Fahrenheit, and Kelvin. Now we'll poke into a bit more detail in each of these measurement ranges. Firstly, Fahrenheit. So Fahrenheit's based on two data points essentially. So point number one, 0 degrees Fahrenheit, is at temperature where a 50-50 mix of ice and a salt will freeze. So it's the freezing temperature of a brine made of ice and salt. Now, of course, because of the offset in there, this is below 0 degrees Celsius. And we know water freezes at 0 degrees Celsius. We also know that if we add salt or salts to water, that actually lowers the freezing temperature. So here we've got a lower freezing temperature than what we have in degrees Celsius. The upper temperature, 96 degrees Fahrenheit, was an estimate of the average temperature of the human body. It was originally, when Fahrenheit first wrote this all down, it was originally 90 degrees Fahrenheit and has been upgraded to a little bit higher. And we should mention that pure water there freezes at 32 degrees Fahrenheit. The Fahrenheit scale has been around a long time, 300 odd years, and was named by Daniel Fahrenheit. It's also worth mentioning that he was the one that invented the glass mercury thermometer that has been commonly used in many places around the world up until quite recently. These days we often use an electronic measure, but some doctors still use a mercury thermometer. Okay, let's move to Celsius then. Now Celsius is based on water, in this case pure water, not the salt water mix that we had, a brine that we had before with the Fahrenheit measurement. And at 0 degrees Celsius, water freezes. At 100 degrees Celsius, or actually just below that, 99.97 degrees Celsius, it boils. But we should also say that it boils at sea level, at standard pressure. that's interesting, because if we go up higher where the pressure is lower, it'll actually boil, water will boil at a lower temperature. So for example, if you go up to the top of Mount Everest, where the pressure is not at near 100 kilopascals, which it is approximately where we are, but more like 34 kilopascals, your boiling temperature of water is about 71 degrees, which is significantly lower, requires significantly less energy than what we require down here. Having said that, it requires a fair bit of energy to get to the top of Mount Everest and to try and keep a fire going on top of Mount Everest as well. Now, this system, the Celsius measurement system, was named after Anders Celsius, and he proposed the Celsius measurement system. His was a bit back to front. So he proposed a system where 0 degrees was where water boiled and 100 degrees was where water froze. After his death, they swapped it around, and so we count up in temperature rather than counting down. I should say there's two different precise measurements of where water boils, depending on the actual pressure that's induced at that point. So whether it's at 1 atmosphere or whether it's at 100 kilopascals, two different measurements, two different standards, but they're very close by to each other. Okay, let's go back even further in time to some of the earliest measurement systems that we know of. So 200 odd BC, we've got Philo of Byzantium, a Greek who lived most of his life in Egypt, who was an inventor, a mechanic, an engineer. He did all sorts of things and wrote a number of books on mechanical systems and siege engines and things like that. He developed this very simple way of trying to sense temperature. He's not doing it on a particular range. There's no scale on this, but he had a ball that had a tube attached to it, and that tube went into a liquid. If it was left in the sun, he noted that he'd have air going out of that tube and making bubbles in the water. And then if it was cooled down and put in the shade, he noted that he would actually draw water in through that tube and into the bowl. And so with this, there was a very rudimentary system of measuring temperature or sensing temperature. Then we fast forward to about 1600, and we have 4 inventors, the most famous of them being Galileo, because of the other work he's done on astronomy. But they invented an air-based bulb-style thermoscope. And the idea was that a liquid, it might have been wine or something like that, so it would be easily seen and contrasted, would be drawn up into that bulb at different temperatures. So at one temperature, it was drawn up by a certain amount, and at a different temperature, it was drawn up by a different amount. We fast forward 50 odd years after that, and we have Ferdinand II, who was the Grand Duke of Tuscany. And his main contribution to all this was that he realized it wasn't just temperature that was a key variable in these measurement systems, it was pressure as well. So rather than having an open bulb at the bottom there where pressure could potentially change, he actually sealed it up and sealed up the glass bulb. And so he developed the first closed system for measuring temperature. And this closed system was less affected by the atmospheric changes that some of the other ones were. Well, after all this comes Lord Kelvin. Now, Kelvin's known for many things. He was a president of the Royal Society. He was a member of the House of Lords in the UK. He was a brilliant physicist. But one of the things that he was investigating was, is there a point where molecules stop vibrating, or what temperature do they stop vibrating at? There were a number of others working in this area, but Lord Kelvin was the first one to accurately calculate what temperature that would be, and that was considered the temperature of absolute zero, where particles have a minimum vibrational motion. So he calculated in the ballpark of minus 273.15 degrees. It wasn't quite that accurate, and that's what we say is absolute zero. Now, the Kelvin measurement scale is based on Lord Kelvin, named after him. And so the zero in Kelvin is this absolute zero measure of minus 273.15 degrees, and we count up from there. Now, have we got there? Well, not quite, but we've gotten within a smidgen of that. The current world record set in 2021 was just over over 0 Kelvin. Prior to this, there was experiments done in space on the International Space Station, where they go also very low, less than 1 degree Kelvin. And then prior to that, we were looking at outer galaxies. that were the coldest thing that we could find. Now, I'll mention a few other temperature laws. Most of these should have been covered in your thermofluids class that you did in second year. So we have Kirchhoff's law, where we're looking at if an object's in thermal equilibrium, the amount of absorption that object will have will equal the amount of emission the object has. We have the Stefan-Boltzmann law, where as an object becomes hotter, the more infrared energy it will emit. And we use that later on for some of our sensors when we're trying to work out how something is based on how much infrared energy it has. Wien's displacement law, we see the graph for it above. The wavelength of the maximum amount of energy that we have becomes shorter as the temperature increases. And so we have graphs there for quite hot temperatures. And finally, we have Planck's equation, where we're looking at the relationship between the spectral emissions that are being emitted from something, the temperature, and the radiant energy of that object. One final thing to think about is difference between temperature and heat. So far we've been talking about temperature, and remember, temperature is a measure of the thermal energy of an object, essentially how hot or cold it is. Now, heat is a form of energy. As we supply heat to something, the vibrational motion of the particles within that object, whether it be a gas or whether it be a solid or a liquid, increases. And the temperature increase of a system is directly proportional to the amount of energy that we put into that system. Now, there's three main ways we classify this energy. One is the BTU, the British thermal unit. And you might see some air conditioners, for example, saying this air conditioner's 5,000 BTU or 10,000 BTU. And they're basically talking about how much energy in terms of thermal energy they can supply as a cooling force. The strict scientific definition is the amount of energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at standard pressure. Now, the SI unit is the calorie unit. And here we're looking at the amount of energy required to raise the temperature by 1 gram of water, so a lot less water, by 1 degree Celsius at a temperature of 4 degrees and at atmospheric pressure. What's often used is the joule as well. And here we're looking, and this is also an SI unit, where we're looking at 1 joule is equal to 1 watt second.